The physical interpretation of the complete response. Let's dive deep into its meaning. Which I will do in steps. So the first thing, we're going to talk about the response of a charging and discharging capacitor. Next, we want to look at the details of the natural and force responses. I mean, there's a third, the complete response, but you'll see that it's just a superposition of those two. And then finally, let's get a visualization about the time constant. Okay, so those are the three things that I want to do. We're going to start off with the response of a charging and discharging capacitor. So we got to break these up into two cases. So the first one I'll deal with is the charging capacitor response. So let's talk about the charging capacitor response. A charging capacitor implies the initial steady state value Vc of 0 minus is smaller than the final one, VOC. In the response equation, the bracket term is negative. In other words, Vc of t, which is equal to VOC plus my bracket term, you could see that the bracket term has to be negative, where Vc of 0 minus VOC has to be negative, and that turns out to be key. So that minus sign doesn't show up so well in the equations. To make this negative sign stand out, I define a new parameter, which is the magnitude of the bracket term. So when I define that, I'm going to say that delta V, and then this is going to be the absolute value of VC of 0 minus VOC. So what you're seeing is that this term is always a positive term. Okay, that term is always a positive term. Where we see that delta V is the difference between the initial and the final steady state values. So what? For a charging capacitor, the response is this now. We're going to write that VC of t, and then I'm going to just write out my term. But now here comes the change. We know that that bracket term has to be negative. So I'm going to come in here and I'm going to put that negative sign in by hand, but that's the magnitude of the bracket term, and this is e to the minus t over tau, and we're saying that this here is the complete response of a charging capacitor. So this is only valid for a charging capacitor. Once again, just to be clear, okay? Once again, the minus sign in front of the exponential term implies a charging capacitor. So I really got to make this stand out. So you got to think minus sign means charging capacitor. A charging capacitor increases its electric potential by climbing up the electrical ramp. So what does this look like graphically? So graphically, here's what I'm seeing. I have a ramp, and let's say that this ramp is going to go something like this. And there's my ramp, and I'm going to say that this ramp here is my ground. So if I'm charging my capacitor, here's what I'm seeing. The total height of this guy is going to be the source voltage. But in a complex circuit, the voltage of the capacitor will never reach the source value. It's going to read it's going to have its VOC value that it's going to do that. So I imagine that I have a capacitor right here, and I'm going to raise my capacitor to a higher energy state. In essence, I have a capacitor that starts here, and when it starts here, this is telling me that I have the voltage measured from the ground is VC of 0 minus. Now, if I'm looking at my capacitor that has climbed up this thing, so for a charging capacitor, you're seeing that I have this height, which is VOC, measured relative to the ground. So as the capacitor goes up, there is an increase. The difference in the height here is what this delta V means. So it's moving in the upward directions like this. What does the RC curve look like now? In the RC curve, I have a very similar curve. And what's happening is that I have my capacitor come in at VC 0 minus. And as the capacitor climbs up, it reaches up to the value of VOC. So if I'm looking at this, this is the maximum voltage that this guy will get. And so if I plot this, you're seeing that I'm getting this behavior. That's that exponential somewhat growth here. And when you're looking at this term represents VC at infinity. So what does the delta symbol tell us here? It tells us that delta V is the difference between these two, and it's in the upward climb that we're talking about. So it's climbing upwards. So that negative sign implies that it is climbing upwards. To get a more of a sense of this, let's look at some simple examples. So let's plot the response for two situations. So in this case, let's say that I'm just going to arbitrarily pick numbers. These numbers are literally just arbitrary. So if I look at this, imagine that I have a response that looks like 5 minus 2 e to the minus t over tau. So the first thing that you should note is that I have a minus sign. The fact that there's a minus sign, it means that it's climbing. That means that there's an increase in voltage. So then the first thing that I note is that this tells me that VOC must be 5 volts. The next thing here is that delta V is equal to 2 volts, and that 2 volts means that there's an upward or an upwards jump to VOC from, so if I made a jump of 2, that means that it had to have started at 3 volts. So picture-wise, how would I draw this? So if I come in here, and I'm looking at this circuit like this, you could imagine that I have my initial steady state, and my initial steady state is VC of 0 minus, which is 3 volts. So when I look at VOC, I'm seeing here that VOC represents VOC, which is 5 volts. So if I look at this, we could see that if I have a charging capacitor, it has to approach this line over here. So what does that delta V mean? Well, it says that there is a difference between the initial and the final that reads delta V equals to 2 volts, but that is an increase of 2 volts from its initial value, and this thing is moving in the upward direction like that. That's what that response means. On the other hand, I could have another example that reads like this. Let's say that I have VC of t, which is equal to 3 minus 10 e to the minus t over tau. Again, this minus sign tells you that I have to have a charging capacitor. So by looking at the equation, we could then say that VOC in this case has to be 3 volts. But the delta V term says that I have to have a 10 volt upward jump to VOC. But if I have a 10 volts jump, then that means it must have started at VC of 0 minus, which then was minus 7 volts. So if I draw this out, I can imagine that I have a circuit that looks something like, not a circuit, but a graph that's going to look like this. So again, I'm plotting VC of t, and of course this is my time. My initial voltage shows that I'm at a steady state, and this is VC of 0 minus, which is minus 7 volts. Then it's going to jump all the way up to here, where I have VOC equal to 3 volts. So if I'm looking at my curve here, you could see that I have to have an upward swing that looks something like that. So again, what does that delta V mean? It means that the difference between these two initial and final state values, that this is a voltage increase of 10-volt increase in the capacitor. Once again, that minus sign is that I have an upward jump. Maybe jump is a bad word, but it goes up like that. Now let's go looking at the discharge capacitor. So it's going to be very similar. So now I have I'm looking at the discharging capacitor response. So it should be clear that a discharging capacitor is the opposite of a charging one. And what I mean by this is that VC of 0 is larger than VOC. This forces the bracket term to be positive where the response is now looking like this. So I can then say that VC of T is now going to be VOC, but now I have a positive, not a negative sign, and this will lead to delta V e to the minus T over tau. And this here is the discharging capacitor. So this is the discharging capacitor equation or response. Now, to be clear, where we define that VC of 0 minus VOC, that this term is a positive term, and that's where you get that sign here. So we said this before, so let's keep doing it for this one here. The positive sign in front of the exponential term implies a discharging capacitor. That decreases its electric potential. So as before, we have to really get these signs right. So I'm going to highlight that, and I'm going to highlight this here. It's easy to mix up that a charging capacitor should have a plus sign, and a discharging capacitor has a negative sign. That turns out to be incorrect. So now let's look at this thing graphically. So when I look at this graphically, I'm going to come up here and I'm going to steal these graphs up here because they will reduce some of our time in writing here. So let me paste these, and then I have to modify these, okay? So what I have to modify is that let's reverse the colors of these now. So if I reverse the colors of these guys, here's what I'm seeing. So what I'm seeing is that the green here represents the initial voltage, and this is, of course, measured relative to the ground. And then the capacitor that has discharged, this guy is our, I can't take this all the way down. This is VOC, and we're measuring from the ground, which I did not put very nicely. So let me clean this up just a bit to make sure I put this on the ground. Okay, so now that's going to be a little bit cleaner. So you're seeing that because it decreases electric potential, there's a downward shift, right? There's a downward shift. So there's a decrease in electric potential. Well, the same thing happens right here. So if I come in here and do the exact same thing, what am I seeing here? Well, what I'm seeing is that I have my initial voltage of the capacitor, and this guy is going to decrease to VOC. So when I'm looking at this, we are finding that I have an exponential decay that's now looking like this here. And so we are literally moving downwards, right? We are moving downwards like this. And that's what I mean by the discharging capacitor here. That's what that delta V. If I see the positive sign, there's a downward shift. So now let's go look at two more examples just to make it nice and clear. So if I look at two more nice examples, and I want to plot the exact same thing as I did before. So I'm going to say that in this example, we're going to say that this is going to be VC of t, and I'm going to have 3 plus 6e to the minus t over tau. Again, not a minus sign. This is a plus sign. A plus sign means that I have a discharging capacitor. So if I look at this, the details, I have VOC is 3 volts. Then if I look at my delta V, I know that there is a 6 volt downward jump to VOC. Now, if I have a downward jump of 6 volts and I end at 3, you know that 3 plus 6 has to mean that it came from 9 volts. So if I look at this graph, I could say that I have a an initial voltage of 9 volts, and this is going to discharge to VOC equals to 3 volts. So if I look at this, I have exponential decay that then comes in and it's going to move from 9 to 3. And the jump from here to here, that jump tells me that it's a delta V equal to 6 volt decrease, meaning that it's moving in the downward direction here. So just one last one here. Suppose we have Vc of t, which is equal to -1 plus 8 e to the minus t over tau. So immediately we conclude that VOC must be minus 1 volt. If I look at my delta V here is 8 volts. So that means that's an 8 volt downward jump to VOC. But you could see that -1 plus 8 gives me 7. So that means here that this voltage initially had to start at 7 volts. So plotting this, here's what I'm seeing. I have an initial voltage of VC of 0 minus of 7 volts. This is going to discharge all the way to VOC equals to -1 volt. So that means that it has to reach this steady line here. So drawing in exponential decay, gotta look something like that. So then I'm looking at my jump. My jump says that I'm going to go down all the way down to -1. So the delta V tells me that's an 8 volt decrease, telling that my curve is now moving downwards, not upwards.